So there's a bunch of different types of regions. I think there's just a bunch of just three. There's one with an upper surface, lower surface, left surface, right surface. Well, for you guys, left surface, right surface. Then a front surface and back surface. We don't really talk about this. It's kind of just like let's intuitively figure out what the bounds are by imagining we're standing inside the solid. Well, rats. What this requires you to do, really regardless of how you think about it, is be able to visualize at least or sketch the solid of integration. So, finding bounds of integration. Representing a solid region E is done conceptually exactly the same way as in the two-dimensional case. Okay, so ask yourself these things when you're trying to figure out what the bounds are that describe a certain region E. Is there an upper surface and a lower surface? So for example, if we have maybe like two planes stacked on top. So that our solid's in between two planes. Upper plane given by z equals g of xy, and lower plane given by z equals f of xy. I just basically stacked two triangles, one on the other. They share a side at the bottom. If that's the case, then you know your z bounds automatically. If so, then z is bounded by the two surfaces. Obviously bounded above by the surface that's on top of the lower surface, which serves the role of the lower bound. To find bounds on x and y, project the solid E into the xy plane. So generally it'll be pretty easy to project in the xy plane because your solid will be like a cylinder, which when you smash it down becomes a solid disk, or it'll be something like a tent, which when you smash it down just becomes whatever its shadow is, which is a triangle in this case. And we already talked about how to find bounds when you're in two spaces, so we won't worry about that. honestly, the problems will usually tell you whether or not there's an upper surface. It'll usually say find the volume that exists between this graph and this graph. It'll say like above the graph or block and below the graph and block. With that kind of language, it's giving you the bounds. The problem's trying to tell you what the bounds are so you don't have to draw a picture and think about it. So look for keywords like above or below. If a solid is above a graph, then it's the lower bound. If it's below a graph, it's that graph placed below the upper bound. So if not, then you can either consider whether or not it's a left surface and a right surface, or a front surface and a back surface. If so, then you can use a similar kind of approach on X and Y. If it's a front surface and a back surface, then the front surface is the upper bound for X, the back surface is the lower bound for X. If it's a left surface and a right surface, then the right surface is an upper bound for Y, and the left surface is a lower bound for Y. Okay. But if none of those things happen, then consider transforming the integral into a different coordinate system. And we had a bunch of those. So the next section is 15.8. It's probably cylindrical coordinates, but I guess they're really random. It's either cylindrical or spherical. Yep, cylindrical. Okay, so cylindrical coordinates.
Bless you.
I'll make some bullet points for this one. When the projection of the solid of integration in the XY plane it is a polar region.
Thank you.
Transforming the polar coordinates expression into gray. Is more easily integrated when in cylindrical. So maybe I'll just so maybe our solid E is this guy located x squared plus y squared is 1. And maybe we're integrating the function e to the x squared plus y squared. So not only is the projection of the solid object in the xy plane a polar region, it's a solid disk, but also the expression inside the integrand is something you can't integrate with respect to x or y. And it's simplified when you use this cylindrical coordinate transformation. In fact, simplify the y. When we write this thing using the cylindrical coordinate system, we maintain the variable z and then trade x and y for r and theta. So z's upper bound beforehand is 3, and its lower bound is x squared plus y squared, but we learned in the polar integral section that x squared plus y squared is r squared. So the lower bound for z becomes r squared here. So then how do we find bounds on r and theta? We project the thing into the xy plane and then see what kind of bounds we would produce for that resulting region. So when we project into the xy plane, we get that little light circle of radius 1 that I sketched in. So then our bounds are from 0 to 1 on r and 0 to 2 on theta. And of course, you can't forget the additional factor of r. Since z remained unchanged and we traded x and y for r and theta, it has the same additional factor as the polar coordinate transformation, which had an integrating factor of r from earlier. So it's the same integrating factor.
Is there a chance we'll have to calculate Jacobian for some reason?
Yeah, if you have a change in variables in multiple integrals, it's not cylindrical or spherical. You'd have to come up with your own.
And that's the partial of each.
We'll get it.
Okay.
Yeah. But you're right. Take my
And then add them together, right?
cross product. Sort of thing. Or not cross product, but determinant of the matrix. It's like a cross product. That's pretty helpful. Next. I'm actually just going to motivate this from the start because folks kind of get a little tripped up on what represents what.
Oh, that's what you mean.
Next one is 0. Okay, so there's 3 variables in the spherical coordinate system. There's rho, phi, and theta, as you all know. So rho measures distance from the origin. And as you know, distance is always big or vary. So in our picture, that would be the straight line distance between the origin and whatever point we're trying to express. If I have more colors in the bag. No, I don't. Okay, actually. Okay.
So is the top one instead of the bottom one?
Pardon?
Is the top one, or is that the same body?
Sure.
Your diagonal?
No,
You got
it'd
this
be the,
diagonal and then this one. You got the XY
No.
diagonal.
This is like a hypotenuse of a right triangle, so it's longer than this side. I'll put it down here. So theta has our usual interpretation. It's just the angle. Oh, that's B. Through which x-axis is rotated counterclockwise.
And it's always on the XY plane.
It's always something you would think about, just like you would think about a polar rotation. And then phi is the sort of the new one. I'll do it in green, I guess. So phi is the angle through which the z-axis is rotated. One way that I characterized it in class was imagine that your shoulder is the origin of some coordinate system, and by default you're facing along the positive portion of the x-axis. If I want to point out a point, then maybe I want to point out whatever that thing is up there. Then I would twist through an angle theta so that I face it. I would lower my arm through an angle phi so that I point towards it, and then I'd extend it out a distance rho so that I actually am touching it. That's the idea of the spherical coordinate system. So by default, phi starts up, pointing directly at the top. Z-axis rotated through 0 degrees, or 0 radians, and then increases, phi increases as you lower it down. Conventionally, we maintain that rho has to be positive, or rather non-negative. Phi. Phi is somewhere between 0 and pi, and then theta is somewhere between 0 and 2 pi. If we increase phi any more, then we have that double counting problem where we rotate one full time around and count the whole solid, then rotate one more time and count the whole solid again. So we only take phi to be between 0 and pi. Okay. So when do we use spherical coordinates?
When you're dealing with the sphere.
Yep.
and when your sphere is located at the origin.
Yep. So we use spherical coordinates when our solid integration is expressed in terms of spheres whose equations will be of the form rho equals a constant, or cones whose equations will be of the form phi equals some angle measurement. Though you can also compute multiple integrals, triple integrals over cones in cylindrical pretty easily too. But if you also have a sphere, then cylindrical doesn't really help you out.
And then the cos, it's row, square, well.
Sign fee.
Yeah, we write down the transformation plans
Yes.
too, everybody forgets those for a reason.
So X is row, sign fee, cosine theta, right?
Yes.
And then row, sign fee, sine theta. And then row, sine fee, sine theta. And then row, cosine fee, right?
No, we're good.
Okay. That's that right. I just forgot the cost. Or did,
Additional.
Okay. That stuff seems vaguely familiar so far. Is anything just like that you guys know about surprise, or is it all kind of straightforward?
it does make more sense now after we've done the other thing, we should go back and look at it again.
Okay, good. Well, the next section is 1510, which people don't like that much. So let's talk about it.
General.
Oh.
General.
Goodness.
How am I coming back?
So we see two specific ways you can change variables and multiple variables. In this section, we just said, you know what, you can do whatever you want, but you gotta pay it. And that's what we're gonna talk about here. So change variables. And multiple variables. When a polar cylindrical spherical coordinate transformation is not enough. We lower the front two boards and raise that one up. Then make your own coordinate system. So, this is that section where you just like get to do whatever you want in terms of defining a new coordinate system. I mean, whatever problem you're working on, easiest, do that. But you have to pay for it. There's a cost associated with changing your coordinate system. So, cost comes in the form of the Jacobian. So the constant changing variables in multiple intervals is given to you by the absolute value of these guys. If you have a hard time remembering the formula, then just notice that the first row is the partial derivative of the first variable with respect to each of the three variables you're changing into.
What happens if you flip that? What if you did like partial of u for the xyz and then partial of v over xyz and then,
Okay.
does the order matter?
Oh, you mean like if you flipped a row, or if you did the u's, v's, and w's in the top, and the x, y's, and z's in the bottom?
Either or.
Okay. Well, if you flip a row, then it won't make a difference. Because what we're gonna do at the end is take the absolute value and changing rows, when computing the determinant of the matrix, just changes its value by a factor of -1. Since we're taking its absolute value, the negative dissolves, and we don't have to worry about it. But, to do this, we need x, y, and z expressed as functions of u, v, and w. If it's easier to just find u, v, and w as functions of x, y, and z, you can calculate the